Hi everyone, welcome to our deep learning introduction. This is going to be a short class based on a course by Udacity called Deep Learning Foundations. Let me just stop this for a second. Okay, so in this deep learning introduction, we are going to discuss things like logistic regression, gradient descent, and data representation, all the building blocks of deep learning. But first, let me start with the machine learning definition. We define machine learning as the programs that write programs, which are used to make decisions without relying on specific instructions from a human. And in this definition, we can see clearly two modules. Programs that write programs would be the training component, and make decisions without relying on specific instructions is the prediction component. In practice, the training process doesn't write programs, but it writes a bunch of numbers that control everything about the prediction process, which is highly parameterized. So we can see these details in the following workflow. Okay, this is not a neural network diagram. This is a typical software flowchart. The circles represent the two processes, training and prediction. The square in the middle represents the knowledge, which is learned from the examples during the training process and coded in these metrics of numbers that we call the model parameters. Whenever we have a question, which is presented by presented here as new data, the prediction process reads the parameters and produces an answer, also known as prediction. For data, we mean a collection of many examples of something we want to learn about. For example, suppose I work at an online retailer and I have historical data on millions of shopping carts. Each cart has several lines with product price, number of units. And we also have the total cost of the cart. To create a retail software that computes the cost of a cart, I have two options. One is to write the specific instructions and have a regular program to execute them. That would be something like, for each line, multiply the price by the units and sum it all up. The second option is to use machine learning. In this case, I would let the training process read all the historical cart examples and synthesize a prediction program that, given a new cart as input, will estimate the cost of the cart. In other words, learn by example. By the way, the problem that where we predict a numerical value is called regression. In our next exercise, we will see other type of machine learning problem called classification, which is when you have to decide between two or more things. For example, yes or no. Okay, now we can define deep learning as a type of machine learning that processes data using multiple layers. And each successive layer uses the output from the previous layer as input. The term depth here refers to the number of layers. One way to implement deep learning is with neural networks. This is a typical neural network diagram. The lines represent a flow of a number. So each line can be one number or a large array of numbers called tensor. The circles called nodes, units, or neurons represent mathematical operations. Each one is a mathematical operation. And since in machine learning we like learning by example, here's another example. Suppose that I have been choosing my online courses based on two pieces of information that I find in a rating site. These are the average rating, 0 to 5 stars, and the number of reviews. So I see Deep Learning Foundations is rated 5 stars with 4,000 reviews. So I took it. Then there is a Scala course rated 1 stars with 1,000 reviews, and I didn't take it. There is also a new TensorFlow course, which is rated 3 stars and has 3,000 reviews. So what is your guess? Will I take it we're going to develop a machine learning model to predict the most likely answer. By the way, this is going to be called a classifier because for each input, it decides to which class it belongs. In this problem, the classes are two, no or yes, which we can represent in a math-friendly way with the binary digits 0 for no and 1 for yes. To build our classifier, we start by collecting a data set. This is a data set of online courses with a rating, the number of reviews, and whether I decided to take the course or not. In machine learning parlance, each line is called an example, and the decision taken is called the label. This type of problem, where we have to learn from a data set that contains a column with the expected output, or label, is called supervised learning, because the machine learning process can compare its prediction with the label, and this is akin to a supervisor giving you feedback. So, to understand how we can model this problem, let's plot each example in a graph with the two input variables as axes, and let's use color to distinguish the classes, where red means no and green means yes. We observe that the green points are above a line, and all the red points are below. So if we draw a straight line, it will separate the two classes. This line is our model. It models the decision criteria that I use to decide which course to take. We say that this data set is linearly separable. To predict whether I will take the TensorFlow course, we plot the example on the graph. Since it falls above the line, that means that the model predicts that I will take the course. The prediction process will output the digit 1. Okay, we just reviewed some foundational concepts. Now, we can take a short tour down algebra lane to help us link the machine learning concepts to the machine learning math. The line here is represented mathematically by a linear equation, ax plus by plus z equals 0, where x and y are the input variables. For example, x can be the rating and y can be the number of reviews. As some of you may remember, in algebra this is known as the standard form of the linear equation. And if you replace x and y in the expression ax plus by plus z with the coordinates of any point that falls on the line, the value of the expression is 0. For any point above the line, the value of the expression is positive. And for points below the line, the value of the expression is negative. The decision that the prediction process needs to take can be represented by a function that outputs 1 if the linear expression is positive, and 0 if the expression is negative. One function that works like that is a logistic function. This is an exponential that converts a large number into a small number in the range of 0 or 1, which can be used to code a yes or no answer, like we need in the classification problem. We shall show how to use a line to create a mathematical model of the decision process. This is called a linear model. The next question is, how does the computer find the line? Well, it uses some properties of linear equations. By making small changes to the constants a, b, and c, you can move the line. For example, if you change the value of c, the line will move away or towards 0, and the other two constants, a and b, control the gradient or angle of the line. So the training algorithm searches for the right line by trial and error. It starts with a random line and counts how many errors this line makes. Then it corrects the line and tries again until the error disappears or does not decrease anymore. A good measure of the error is to count the misclassified examples in the data. So later we will see other ways to measure error that are better because they are differentiable. So to decide which way to move the line for the next try, the training algorithm we'll move it a tiny bit, for example, 1/10 of a step in one direction and recomputes the error. So here we see that the error decreases. So if the error decreases, we will move the line a whole step in the same direction. If the error increases, we would have moved the line a whole step in the opposite direction. So the method that I am describing to search the line is called gradient descent, and it's a class of optimization algorithm which, with some variations and enhancements, is the silver bullet used to train all kinds of deep learning models. The decision model, based on a line and a function that outputs 0 or 1, is called logistic regression. And it's the math operation that runs in each node in a neural network. Okay, all the things discussed so far are ordinary machine learning, not deep learning. Deep learning starts now. The logistic regression method works well if the points can be separated by line. But in our exercise, that would mean that if the number of reviews is very high, I would enroll in the course, even if the rating is 0. That doesn't make sense. So let's update the graph to reflect this fact. Now we have a problem because the points cannot be separated with a straight line. We could try with a curve like a circle, or we could also try with 2 or more lines. Let's try with 2 straight lines. I call them M1 and M2 here. These 2 lines divide the graph in 4 regions. So 1, 2, 3, and 4. Each line in isolation makes some errors, but in combination, the 2 lines separate the classes without error. So note that all the green points are in the region that is above both lines. Note that this is equivalent to saying that the green points are in the region that is above line M1 and above line M2. So let's assume that we build the 2 logistic regression models, each with a line as a graph. When we input our question, represented by the rating and the number of reviews in the test example, each logistic regression model will output 0 or 1, depending on whether the point falls below or above the line, right? In this particular problem, we can separate the 2 classes by combining the output of these 2 logistic regression models with an AND operation, which is shown in the table on the right. But AND is a specific instruction. What I mean here is that in other problems, we may need a different logical operation, like OR. So to create a generic model that works for many problems, we should be true to that part of the definition of machine learning that says without specific instructions. Okay, let's recap a bit. We use 2 logistic regression models to transform the input variables into a pair of binary digits, which together they indicate the region of the graph where the point is. If we compute the output of the 2 logistic regression models for all the examples, we can draw a new graph, which will have the binary outputs as axes of a new coordinate system. So here's the graph, and here's the nice part. In this graph, the points are linearly separable. That means that we can find a line that separates the 2 classes without error in this graph. This would be a third model, one that uses the output from the 2 models in the previous slide as input. Okay, here are the 3 models. Together they form a neural network with 2 layers. Each node is a logistic regression model, and they can be trained all together. This type of neural network is the simplest kind and is called a perceptron or multi-layer perceptron, MLP, because it has more than one layer. Now, if the process, if we reprocess the TensorFlow example, we obtain two ones as the output of the first layer, and we can call this array the data representation of the TensorFlow example. After passing through the first layer, this is also known as a feature vector, by the way. In the second layer, a third logistic regression node can learn a linear model that classifies these two ones as an example of class 1. So I've been calling these numbers binary numbers, but the logistic regression function, it can give you something that is a little bit less than 1 or a little bit more than 0. But in general, most of the numbers will be very close to 0 and very close to 1. So we have reached the end of the lesson. So it's time for a quick recap. We have a data set with each example represented by two variables, rating and number of reviews, and the output decision, also known as label, which can be one of two classes, yes or no, 1 or 0. We plot these examples in a scatter plot with the two input variables at axis and the color red or green representing the class. Then we model the decision-making process mathematically, representing the decision criteria with a linear equation and the output class by the digits 0 or 1. We then discuss an algorithm to search for the line that best separates the points. We mentioned that the linear equation is defined by 3 constants, also known as model parameters or weights. We then recognize that our problem may not be linearly separable and came up with the idea of finding 2 lines that are enough to separate the points. We call the 2 points of these 2 models in the first layer, we call the outputs data representation, a data representation of the original points. Finally, we added a third model that takes as input the output of the 2 previous ones and finds a line that separates red and green points in the new representation graph. Okay, one last thing. This slide shows the resemblance of the model we built with human neuronal networks. We can see a neuron that takes signals from 2 adjacent neurons and decides whether to activate. Okay? We're really done now. I have some time for questions, so please go ahead and ask me now or email me later. Okay, in this lesson, we have discussed deep learning, machine learning, regression, classification, supervised learning, linear model, nonlinear models, logistic regression, gradient descent, model parameters, data representations, and neural networks. The most important concept for you to pick up, though, is how the logistic regression model can be applied recursively in a layered fashion to separate classes that are non-linearly separable. Okay, all the computational details have been largely omitted in the interest of conceptual clarity. So in the next few lessons, we will map each one of the algorithmic steps to the specific mathematical operations. This lesson was just the glue that holds all those concepts together. I hope to see you in the next module to dive in the math. Okay.